Okay, everybody, welcome back. Today we're going to be actually compiling and building our model and saving it. So I want to make one small correction. So if you remember last video, I called this a max pool 2D layer. That's actually like an alias, a type alias for a max pooling 2D, but this is going to give us a problem probably. So actually the correct syntax here should be max pooling with an ing on the end, so make sure you fix that. And then I also realized I didn't explain the flatten layer, and I want to do that just for the sake of completion so that you totally understand what all these layers are doing. So we talked about all the other layers. Let me just jump over here. So really quickly, let me just explain what the flatten layer is. It's very simple. So if we have an image like this, and let's say it's 3 rows and 3 columns, so 9 pixels, let's just say for simplicity. And then we have a dense layer over here. So I've got let's say my dense layer is 5 nodes. Ours is 128, but just for the image. And what the flatten operation or the flatten layer is going to do is it's basically going to cut this into strips. So it's going to cut each of these rows out. So that's the first row. This is the second row. Here's the third row. And what it's going to do is it's going to paste them into a single column vector. So like this. So imagine you just took an image and you just sliced it up into strips, and then you taped all those strips together into one long column. And the reason we're doing that is you can, if you remember, each of these is 3 by 3. This one, I made an extra line here. Let me fix that. So here's so each of these rows has 3 columns, and now we've lined them all up into a strip. And the reason we're doing that is we want to tie this into our dense layer. So the dense layer, if you remember, is this thing is every item is going to connect to every thing. So that first element is going to connect to every downstream dense element, and then the next one's going to be the same. So it's very dense. That's why it's called the dense layer. So the reason we're using that flattening layer is basically so that we have the correct dimensionality. We want to be able to map this 3 by 3 matrix to a column of nodes. And to do that, we're basically turning it into this column vector. So that's what the flatten operation is doing. So that's very easy to understand. Okay, so let's go down to our main here, and we want to actually start building our model. So first thing we're going to do is we're going to have to call a shape on this gen model function, and the shape is we have to add image channels 3, and the reason is the shape of our image data is not 180 by 180 pixels. It is 180 by 180 pixels. But each pixel is made up of 3 values, R, G, and B. So the actual shape of our data is 180 by 180 by 3. So you can almost think of it as a 3-dimensional object. So make sure we add this as a constant. And then what we're going to do is we're actually going to generate our model. We're going to actually generate it. So down here we'll say model equals gen model. And we're going to put in our shape. So our shape is going to be height by width. Oops, image width. If I can type here. And then by our channel count. So it's 3-dimensional. Okay. And that will create our model architecture, if you will. Next, we have to actually compile our model, and compiling is quite simple. So what we're going to do is we're going to say model.compile, and this is a function. And this function is going to take there's a few different arguments that we're going to want to put in. The first we're going to want to put in is our optimizer. So the optimizer is the type of function that is used, the type of method for minimizing loss. And there's some different ones like gradient descent. The tutorial is using one called Atom, so that's what we're going to use. And we can discuss later about some different optimizers. Next, we're going to we're going to want to specify the loss. And the loss is going to be Keras, in this case, Keras.losses. And then sparse, this is a long one, so it's sparse categorical cross entropy. And from logits equals true. So that's a long one. Make sure you get that one typed in correctly. And then metrics, we're going to say is accuracy, which is how accurate our model is. And this is a list, so we could put in others as well. So we'll say accuracy. Okay, so this will compile our model. And then next we want to build our model. So we'll say model.build. That's very simple. So you can think of that compiling and build step kind of, related. And then finally, let's actually display what our model looks like to make sure it looks like it's been compiled properly. So we'll say model.summary. And what this will do is this will print some information about our model to the console. So I'm going to go ahead and run this now. I'm going to go into my terminal here. You can run this right within code if you'd like, or whatever IDE you're using. But I just want to give you an idea of, oh, looks like I got a typo. So I'll copy that. I must have typed this in wrong. Save it. Let me try to run that again. Make sure you type that in. That's a, a long one. Okay, so it compiled my model. So like before, we have our classes here, but here's the new information. So it compiled my model. Let me make this a little bit bigger. So it compiled the model, and it's creating for me like a list of layers and also the number of parameters. So we have our rescaling layer, which of course is going to take our image in the dimension of 180 by 180 by 3. Okay, then we have a convolution 2D layer, and that's going to have this the same input as this one's output, of course. So this is going to feed into this. But if you remember, we specified the output size on this as 16, 32, and 64 respectively. So you can see that the output size of this convolution is now different, which makes sense because in our code we specified 16, 32, and 64 filters. And then next, after this will feed into our max pooling 2D layer. And if you notice, the output size of our max pooling 2D layer is a lot smaller. And like we discussed, that makes sense because what it's effectively doing is it's combining those elements in selecting the maximum value within that window. So it's basically downsampling the image, and each time it's being downsampled. So that makes sense. So we have 90, 90, 16 that feeds into here, gets downsampled. Now we have a 45 by 45 feeds into here. Now it gets downsampled. Now we have a 22 by 22. Finally, this gets flattened into a single parameter. So let's see if I take out my calculator here. So if I did 22 times 22 times 64, that is 3976. So again, this is just taking all of these and basically turning them into a single row, a single column. So that's why my flatten operation is giving me 30,976 elements. And then that's going to feed into my dense layer. So every single one of these is going to connect to every single one of these. And this is where the model starts to really explode in size. Now I have maybe 3.9 million or so combinations here. And then finally, this is going to feed into the final dense layer, which is 5, and it's size 5 because each one of these corresponds to one of these. So the first one is a daisy, the next one is a dandelion, etc. And altogether, we have 3.989 million parameters that can be tuned. So you can see that this model has a lot of different multivariables that can be modified. But it looks like our model is working correctly, and I believe this matches the tutorial. Well, let's see here. Yeah, so 3.9 million. So that's good. So we're on the same page as those guys are. So that's good. So let's get back into code here. So essentially we've built our model, we've compiled it, and we just displayed it. So the model is there. The model is like a child now. It's got no information, it's got no learning, and it's ready to learn. So in the next video, we're going to actually start fitting or teaching our model. It's going to start learning. And then in the following video, we'll be able to start testing our model against brand new images. So this is getting pretty exciting. So see you in the next video.